Okay, guys, how's it going? So we are now commencing our beginning of chapter 15, and what that means is that we're going to be learning an entirely new concept called equilibrium, and it turns out that this idea stays with us for the remainder of the course. So it's like hyper important that we understand this, and I'm going to make sure I take my time with this chapter because the fundamentals. I guess what I'll say from the beginning is that this is not a very difficult chapter necessarily, but you are learning some very fundamental properties of equilibrium that will stay with you the entirety of the course. So at the very last chapter, we're still going to be calculating equilibrium constants. So make sure that you understand really what it means for something, like interpreting the equilibrium constant, understanding it at a very deep conceptual level. So the best way to do that would be to do just an incredible amount of problems to get to that level. So I guess we'll first start off with number one. So we have a mixture of zero point 0.1 mole of NO, 0.05 mole of H2, and zero point 0.1 mole of H2O. It's placed in a 1 liter flask, and it's allowed to reach equilibrium as shown in this equation here. So you know it's at equilibrium because I have this double-sided arrow here. Okay, so at equilibrium, you have a concentration of NO that's 0.062 molar. Calculate the equilibrium constant Kc for this reaction. Okay, so probably the first thing that would be very important here would be to first write what the equilibrium constant expression would be for this reaction. So let's do that. So if we did that, we would have to write that, hopefully this doesn't get cut off, so it would be Kc is equal to, I'll just write it very generally at first, that the products over your reactants, right? And in this case, we're going to get a little more fancy because we actually have an equation. And the way we do that is we raise the products to their coefficients. So N2 has a coefficient of 1. I'm writing it just for like instruction purposes. You don't need to include the 1 if you don't want to. And then you have H2O risen to the second power. And then you have NO to the second power, followed by H2 to the second power. So a lot of things raised to the second power. So this right here is our equilibrium constant expression. And it's really worth pointing out that the numbers, the concentrations, remember concentrations are represented by the brackets that we see here. The concentrations that are inputted into this equation are all equilibrium concentrations. Now it's like super important to recognize the fact that most of the time when they do these kind of reactions, you're normally given the initial concentration at some point, or maybe you're given like how much it changes, but really the only thing that goes in this is going to be the value that corresponds to the concentration of one of these reactants or products at equilibrium. So ensure that you never put anything else than any other concentration that's at equilibrium when you that goes in those brackets in this Kc equation, okay? So what does that mean? So let's take a look at our problem again. We have a mixture with initial conditions of 0.1 mole NO and H2, and it's allowed to reach equilibrium. So it says at equilibrium you're given your concentration of NO. Oh, so that means we know this component of this. We know the NO. We just don't know everything else. So to get the other reactants and products, we have to do kind of like a mini ice table. And this is a concept that by the time you're watching this, you probably would have been introduced to. At the time I'm filming this, you have yet to learn this topic. But I'm going to speak about it as though you've been exposed to it in the past. So we're now going to do what's called an ice table. And the way we write that is we write out our expression, 2NO plus 2H2 and 2 plus 2H2O. We just write out our expression. We write a row corresponding to the initial concentrations, the change, and the equilibrium concentrations. Now I want to be really clear that the entries of this that go into these rows and columns all of these are concentrations. We don't use moles. We have to divide by the total volume to put concentrations in here. So just to be clear, molarity, capital M, is equal to moles per liter of solution. So a lot of the times students will kind of mess up and they'll not divide by the total volume of the solution. Ensure that you are inputting molarities, concentrations, into this ICE table, not moles. Okay, we'll use moles at a different time, but that's not what we're doing right now. Okay, so we need to recognize the fact that we have this like flask, right? And it's 1 liter in volume, and I'm inputting the 0.1 moles, the 0.05, and the 0.10 moles. And in a way, if you are solving for molarity, it's moles per liter. We're really just dividing all of the moles by 1. So we can kind of think of 0.1 mole as 0.1 molar, and so on and so forth. But I will say that oftentimes it's not in 1 liter. You'll have to accommodate by dividing by some number that represents the total volume. Okay. All right, so what's my initial conditions? Well, I have 0.1 molar of NO. I have 0.50, apologize, of N2, and 0.1 molar of H2O. And that would imply that I have let's see, a mixture of that much. Oh, I'm sorry, I kind of screwed that up. 0.05 mole of H2. Sorry, that goes here. I have no N2. I have none of that to begin with, so 0 to starting with. Okay, and then we see at the equilibrium, so I'm using all the numbers they gave me at this point. And only other number they gave me was this 0.062 molar, and that's the equilibrium concentration of NO. So then I know that this went down to 0.062. So what happened? What happened here? Well, as expected, your reactant's concentration went down. That's what happens to reactants as the reaction proceeds forward, right? You lose a little bit of reactant. But by how much? So the way we can do that is by getting the difference between 0.1 and 0.062 minus 0.062. I'm not going to do it in my head. And the number that you get here, I'm going to put in a different color because it's important, is 0.038. That is the amount of which by which we've changed in molarity. Now it's worth noting that the C in ICE table stands for change. I'm sure you guys know that already. I need to get out of this mindset that you've already seen this. So the C stands for change, and E stands for the equilibrium concentration. And here's the beautiful thing. The fact that I know that this amount changed by 0.038, that means that I can solve for the remainder of all of these things. So what do I mean by that? I mean that because NO changed by a factor of 0.038, and I know that H2 and NO both have the same coefficients, well then we know then through kinetics that their rate of loss will be the same. So therefore, then this will also lose by a factor of 0.038. Okay, and then there is a coefficient of 1 in front of this N2 that I should probably just point to with this little laser, right? There's a coefficient of 1 here, and then using our kinetics, sorry I forgot the 8 here, we need to be cognizant of the fact that the rate of formation of N2 will be half that of the loss of NO because of the 2-to-1 ratio. So this is why we learn these things in the first chapter. So then what's 0.038 divided by 2? I'm just not in a math mood, I guess, right now, so I'm just going to do everything in my calculator. So that's minus, or rather, since it's a product, we're forming it, so it's going to be a plus 0.019. Oh, and then we can see, well, what is the ratio of H2O and N2? Well, it's also H2O and NO. Well, it's a 2 to 2. It's the same ratio. So I'm going to gain by the same amount, 0.038. So hopefully that's making sense. The amount by which there is a change relies heavily on the coefficients in the balanced chemical equation. And that brings up a really important point, that you always want to make sure, I'll put this in a little, or actually write this, ensure reaction is balanced. Okay? If it's not balanced, you can see very clearly that you will fail the problem at this stage, right? There is a very strong reliance on the equation being balanced at this stage. Okay? All right, so then all we got to do is do a little bit of math. So 0.05 minus 0.038 minus 0.038. If you do that, you get 0.012, 0.019, and 0.138. All right, so then I have my equilibrium concentrations, right? That's this final row in this ICE table represents the equilibrium concentrations. I will write that down because it's very important. This final row represents the equilibrium concentrations. Therefore, the numbers that are in that final row can be inputted into this expression here to the left. Remember, I said earlier that only equilibrium concentrations are inputted in there, and you've literally just solved for them using the ICE table. That is the utility of the ICE table. Oftentimes, students don't connect those dots. They're just doing ICE tables. They know how to do it. They can make the table, but they don't understand that the output of the ICE table represents equilibrium concentrations, and those can be plugged into the KC. Okay, so hopefully you guys are like the first class that understands that perfectly. I want to it's going to be ingrained into you, hopefully. So because we have those, I'm going to erase this, and I'm going to do another KC expression. Sorry, this is getting quite cluttered. I'm sure if you're following along, it's kind of a lot. So then what's my concentration of N2 at equilibrium? 0.019. My concentration of H2O is 0.138. We've got to be careful. Remember that there's a square here. There's a square here, so don't drop it. Make sure you don't forget that. Concentration of NO at equilibrium is 0.062. And that's going to get squared as well. And then H2 has a concentration of 0.012. And we're squaring them. Then finally, I can just plug this in, and we will be done. 0.19, 0.138 squared. Okay, so I plugged that in, and the value that was shot out is 6536.8. And then we just need to accommodate it for significant figures, which there happens to be 2. So then my K is going to be equal to 6,500. Alrighty. So, what did we do here? We did our first equilibrium problem, but more importantly, what we did is we kind of connected the dots, hopefully, between ICE tables and solving for the equilibrium constant. Okay. We made sure that we rose all of the concentrations at equilibrium to their respective coefficients in the balanced equation. But yeah, that's pretty much it for this reaction. Let's see. I guess the last thing we could do, just to really kind of get everything, squeeze every little ounce of knowledge out of this problem, would be to look at the equilibrium constant, Kc, is 6,500. So how do we interpret that, right? Well, in class, at least today when I'm filming this, today you learned that because Kc has a value that's much greater than 10, then it would imply, maybe pause the video and try to think, are the products or the reactants favored? Pause the video and think about that. Are the products or the reactants favored? Okay, hopefully you paused and thought about it. Well, because our answer, our K, is very large, and K represents the products over the reactants, the ratio of the products over the reactants. Because we have a large value, it would imply that at equilibrium, at EQ, products favored. Okay, well, I think we've squeezed just about everything we can out of this problem. I think it's a very great problem to get us introduced into the concepts of KC. And I'm going to hopefully go through most of these Chapter 5 review question problems for you, so you have somebody working with you given this remote environment, okay? So I hope this was helpful. Thank you guys for your input. I think it's been a really great experience trying to figure out how to navigate this, and I think it's an enjoyable experience overall. Okay, I'll see you in the next one. Study hard.